is Maciej, and I'm currently a PhD student at the University of Strathclyde in Glasgow. I'm also a member of the Strathclyde student community for optics, physics, and engineering, or SCOPE in short. Just before I begin, SCOPE is a postgraduate student society aiming to connect students in STEM and with the goal of helping them with personal and professional development, and with the goal of also spreading our passion for science with general public by the means of outreach activities. So for today, I will show you how to do a simple experiment at home which will allow you to determine the speed of light. You might have heard that light actually travels so fast that it can go around the Earth's circumference almost 8 times per single second. So we must be thinking that there's no way you can measure speed of light at home when it moves so fast. Well, here's a twist. You can. And you actually only need a few things to do that. So for this simple experiment, what you will need is a bar of chocolate, a microwave, a microwave safe plate or a bowl, a ruler to measure, and a scientific calculator like the one you can have at your phone. So, as you might know, radio waves, visible light, microwaves, X-rays, or even hard gamma radiation in space are all forms of electromagnetic radiation. All of these forms of radiation differ in their wavelength, which defines the energy of the radiation. Shorter wavelength radiation typically has higher energy. So what we will do is we will be using the equation speed of light equals the frequency of the radiation times its wavelength to estimate the speed of light c, and we will be using the frequency of microwaves and the wavelength of the microwaves in your microwave. So what we will do is that we will use this simple bar of chocolate to kind of record the wavelength of the microwaves that are present in the microwave. So first of all, some important things about the experiment. During the experiment, the plate that's in the microwave must not rotate. So in case you have a rotating plate in your microwave, you need to take it out, and the chocolate must be placed in kind of fixed, non-moving position throughout the experiment. So what you can do, and what I have done as well, you can use like a bowl and kind of cover the rotating part of the microwave with the bowl. And then you can place your plate at the top, and you can place the chocolate there. The microwave should include, presumably inside, a small label which tells you the frequency of the microwaves used in the oven. Unfortunately, mine did not include it, but I think yours might, because it should be there. The label will tell you the frequency in either gigahertz, which is billions of hertz, or in megahertz, which is millions of hertz. If it's not there, don't worry. Microwave ovens usually operate at 2.45 gigahertz. So you just place your chocolate in a fixed position in the microwave oven, and you put it on maximum power and just microwave it for a short period of time. The length of the time depends on the model. For me, it was about 30 seconds, but I would recommend trying, let's say, 10-second increments, and after each, check if you see any changes to the surface of the chocolate. So what will happen, what also happened to me, is that you will notice that the chocolate will melt, but in certain places it will melt a lot. So I guess it's kind of hard to see, But for me, it melted in these two localized spots. So one is here and one is here. So what do you think is the reason for this? It's quite a strange behavior. Why does the chocolate only melt in discrete spots on the surface? Why doesn't it melt evenly everywhere? Maybe you can stop the video and try to figure out what could be the reason. I'll just mention one thing here, is that the microwaves are actually waves. So the microwave oven is designed in a way that the waves create something called a standing wave. So the standing wave is fixed in the space in the microwave like this. It doesn't move. So it doesn't move in space, but it still oscillates. It's still a wave. So what it means is that these red spots, which are called the nodes, are fixed. These don't move. While the maxima and the minima of the wave, these are called the antinodes, these move a lot. So the wave has places where it doesn't move at all, the nodes, and it also has places where it moves a lot. So there's lots of energy in these spots. Maybe this will be helpful for you to uncover the mystery of the melting spots in the chocolate. So, after measuring the distance between the spots on my chocolate, the value I have obtained was approximately between 5.5 and 6 centimeters. Obviously, getting a precise value is quite challenging because the melted spot can be quite large and it's hard to say, let's say, where is the middle of the spot. So if you want to get higher confidence value, what you can do is repeat the experiment multiple times. Let's say place the chocolate in slightly different positions, measure the value of distance multiple times, and then let's say take a simple average of the values. And this will give you higher confidence that the value you have obtained is what you actually wanted to measure. And this is a typical example how measurement uncertainty can be improved in science. It's also important to mention that for the final equation, for the final calculation, the wavelength should be in meters. So if you measure it in centimeters, you need to shift it to decimals. So what's actually happening here is that the distance on the chocolate between the two melted spots is the distance between the two neighbor antinodes. Let's say in my case it would be this one and this one. What that means is that the distance you have just measured is essentially half of the wavelength. So my value was about 6 centimeters, which means the wavelength of the waves I have measured with the chocolate is 12 centimeters or 0.12 meters. So let's put all of these values together. So the wavelength of, let's say the distance between the spots that I have measured, 0.06 meters, times 2 to get the wavelength, times 2.45 times 10 to the power of 9, 2.45 gigahertz. And if we multiply these values, what we actually obtain is 294 million meters per second. And this is actually really good because the actual speed of light is 299,792,458 meters per second. So the value we have just obtained is extremely close, which means by using a chocolate in a microwave, you have just measured the speed of light. Congratulations. And as a sweet reward for your hard work, you now have a chocolate, which you have to eat. So, thank you very much for joining us for this experiment. I hope you enjoyed it, and I hope you learned something new about waves.